Okay, in this video I'd like to talk about how to find a column space of a matrix. So we have a theorem that says the columns of A, which correspond to columns of reduced row echelon form of A, which have a leading 1, would end up forming a basis for the column space of A. So let me first talk you through how to do it this way, and then I'll describe an alternative. Okay, so given a matrix A and its row reduced form, this is actually the same matrix from the previous video. We look at which columns in RREF have a leading 1. So this is a leading 1. These each are the first non-zero entry in their row. So these three entries. And so you look at which columns they appear in. They appear in columns 1, 2, and 3. And so columns 1, 2, and 3 of the original base of the original matrix are going to form a basis of the column space. So our basis of column space is going to be the columns which correspond to leading ones. So 1, 2, 1, 0, 2, 1, 0, 1, and 3, 1, 1, 0. Okay, so that's probably the easiest way because we have a nice way to find reduced row echelon form. We just type it in type it in a calculator or computer software. Another alternative, if we wanted to find the column space, is that the column space of A would actually be the row space of A transpose. So just imagine if we took the transpose of A, then each of these that I've written as a column would be a row. And so that's another way that we could find a column space, is just by taking a transpose and then row reducing to find the row space of your transpose, because the transpose of a row would be a column. Okay, but again, probably this method that I've described with this theorem is the quickest way to find the column space, or at least find at least a basis of the column space. Okay, so as another example, let's look at the matrix B from the previous video. We have the row reduced form, and then we look at which columns have leading ones. So we have two leading ones, and those are showing up in the first and second columns. So we want to go back to the original B matrix, not this matrix anymore, just the original matrix, and where are those columns? So the corresponding columns in the original matrix. So our basis of the column space is going to be 1, 2, 0, and 2, negative 1, 3. Okay. Let's try one more example. Given a matrix C and its row reduced form, we look at where are the leading ones. This is the first non-zero entry in each row should be a 1 if it's in reduced row echelon form. Also has zeros above those ones, but mainly where are the leading ones at. So this is in column 1 and column 3. So column 1 and column 3 are going to be a basis for the column space. So 1, 2, negative 1 as the first column, and 1, negative 3, 3 as the third column. Okay, so I said there's a second option, which is to take the transpose and then row reduce. If you do that, you probably won't get the same basis, but it should still be an equivalent basis. So there's more than one ways to complete the problem. There's more than one correct answer. We do know, however, that the dimension is fixed, so the dimension should be the same. And we also had a theorem which said that the dimension of the row space and the dimension of the column space should both be the same, and they should both be the rank of the matrix A. And so one way to think about that is that the rank is the number of non-zero rows in your row reduced form. So when we row reduce, these two rows would be our basis of the row space. The columns corresponding to leading ones would be a basis for the column space. Either way, the number of leading ones, in this case 2 and 3, would be the number of vectors in the row space, the number of vectors in a basis of the row space or the column space, which would also be the rank.